Hi, my name is Nick Kern. I am a Hubble Fellow at the University of Michigan, and today I'll be talking about my research at the intersection of high redshift cosmology, astrophysics, and Bayesian inference, specifically for 21 centimeter cosmology. So I'll motivate a little bit the 21 centimeter cosmology science, which is that there's, to date, a wide range of redshifts where we have systematically uncharted cosmological information that's going to help us shed light on some outstanding problems in standard model cosmology and high redshift astrophysics. So neutral hydrogen is an abundant tracer of large-scale structure. It emits, due to its spin flap transition, a radio wave at 21 centimeter in wavelength, and we can use that hyperfine spin flip transition, the 21 centimeter line, as a probe of the growth of structure. And in particular, because it's a spectral line, we can use it as a tomographic probe over cosmic time. Right? So at low redshift, redshift below 5, neutral hydrogen is locked up in the ISM of galaxies, and it's used as a bias tracer of the density field to do large-scale structure and fundamental cosmology. At high redshifts above 6, before the epoch of ionization has finished, most of the neutral hydrogen is in the intergalactic medium, the space between galaxies. And as such, it's a sensitive probe of the formation of the first stars in galaxies. So these sources created UV photons and X-rays, which then propagated through the IGM, affecting its ionization and temperature state, which we're sensitive to with radio telescopes. So, given all of the scientific potential that's there for 21 centimeter to extract, there have been a lot of experiments that have been designed and built, commissioned, to go after the signal, both at low redshifts below 5, and high redshifts above 6. So we've got about 5 to 10 years worth of data sitting on disk as a community, and we spent a lot of time looking at how to analyze this data. Furthermore, coming online in the next 5-10 years, we have experiments, next-gen experiments like the SKA, that will take this to the whole next level. And the question you may have is, okay, what have we learned so far from 21 centimeter? And the answer is we have learned some things, but we haven't done the majority of the science that we'd like to do yet. And that's in part because we're still hindered by foregrounds and systematics. So what's preventing direct signal detections? The first is we have a weak signal, fundamentally, that takes long integrations to detect, but more importantly, a signal that's masked by incredibly bright foregrounds, particularly at low frequencies. So at these low radio frequencies, what we see predominantly is non-thermal synchrotron emission that's about 10 to the 5 times brighter than that background cosmological signal that we're looking for. And this is all rounded out by the fact that this is modulated by a complex instrumental response that we don't know perfectly. And really the challenge here is understanding that instrumental response to 1 part in 10 to the 5 in order to perform this very delicate signal separation problem. Okay, so but what do we know so far? And it turns out we have learned some very interesting things about particularly the high redshift universe just with upper limits. So what I'm showing you here are the best upper limits on the EOR 21 centimeter power spectrum prior to 2022. And what you're seeing is that over the past 5-10 years, we've made steady progress in marching down in this parameter space and excluding power spectrum models of higher and higher amplitude. In 2022, the Hera collaboration, the collaboration that I'm a part of that I'll be talking about a little bit today, put out its first limits from part of its season 1 data. This was an analysis that I led during my PhD and my first postdoc that set world-leading limits at redshift 8 in particular. And redshift 8 is over an order of magnitude improvement over existing limits. And what we were able to do is to show for the first time, convincingly, that the IGM had been heated above its adiabatic cooling limit. And what this meant is that it in some way allowed us to constrain the production of the first X-ray sources above redshift 8. Which is the first indirect constraints on these kinds of astrophysics that we've been able to do so far. So a year later, we went back with a little bit more data, and we were able to improve these constraints by about a factor of 2. And to date, those limits are still the most sensitive constraints on the EOR power spectrum. But you can see we're about still an order or 2 magnitude away from these fiducial theories. And so the question is, what's going to get us there? Well, one, we're taking more data with Hera, and we're analyzing our most sensitive data set to date. And we're going to continue to do that to push down in sensitivity and to push out in redshift as well. But once we get down to those sensitivities, the real question is, how do we deal with systematics, and how do we make a robust direct detection as opposed to just upper limits? And that's going to be the focus of my talk today. So to motivate that, I'll tell you a little bit about the problem we face with a kind of mock data set. So this is a toy model data set that I put together showing you the kinds of signals in our data in Fourier space. So you can think of this as like the square root of the power spectrum. So there are foregrounds, we know that. They're very bright, but they're spectrally smooth. And that means in Fourier space, they occupy a narrow range of K-modes. We also have noise, which is, to very good approximation, normally distributed and uncorrelated. And so the name of the game for these 21 centimeter telescopes is to integrate down that noise. So going back to the same part of the sky every single day until we make some kind of measurement of the underlying EOR power spectrum shown in green. Now, that power spectrum has support across a wide range of K-modes because as a function of line of sight, you're probing the inhomogeneities of the IGM. Okay, so it turns out if this was the picture, we would probably already have detections, right? So we integrate down the noise. We do something with the foregrounds. Typically what we do is we filter them out. We say we don't really think we can subtract them to this required tolerance, so we're going to filter that out. Some experiments choose to do some kinds of direct modeling and subtraction to make this a little easier, but more or less, most experiments do some form of filtering at some degree. And so this is called foreground avoidance. And if this was all there was to it, we would already have pretty convincing detections, I think. The problem is that, of course, systematics come in and kind of make this more complicated. So systematics, like, for example, the chromatic response of the instrument or the beam, take this simple picture and they make it a little more complicated by convolving the foregrounds with this kernel shown in red. And so now the foregrounds in your data is not the foregrounds in blue, it's the kind of convolved foregrounds in red. And the problem is that kernel, that red systematics kernel, is fairly uncertain. So we don't know exactly what it looks like. And so if we were to make measurements, say, of our data, we would measure something that might be something that looks like this in black. Right, and so we would measure some systematics and maybe some signal at high K, but we don't have a really good understanding about that transition. And we might say, well, okay, we know these points right at the edge of this foreground wedge here. We think those are probably systematic dominated. We don't think that, we think this is a little too high to be an EOR signal, so let's filter some of these modes out, right? And we would just cut them. And so you can see this is a little bit of a roundabout way of making power spectrum measurements, and it's certainly not a way to make a detection. It is a way to make an upper limit. So you can set statistically sound upper limits this way, basically saying, I know that the EOR signal can't be above this point, but there's no constraint on where it is below this point. And we can do science. As I mentioned, we've been able to do some really interesting science about high redshift IGM heating models that has been inaccessible from all other probes to date. But the kind of science we want to do with 21 centimeter long term, we really need direct detections. That's the transformational science that we hope to do. And to do that, we need to be able to do this a little more robustly. And so instead of simply cutting out more data, we do have statistical jackknife tests that help us, informs us about whether these points are more or less systematic in nature. But what we would really like to do is to say, how can we actually set error bars better? And not just thermal noise error bars, which we know how to do pretty well, but how do we marginalize over our uncertainty in this red kernel? Basically, how do we marginalize over our uncertainty in the systematics? And that marginalization will naturally lead to error bars that are inflated in the regions that are systematics dominated, and error bars that are smaller in regions that are not systematic dominated. However, this has been traditionally very computationally costly, so it's been infeasible. But as we look towards the future and say, what are the next gen analysis frameworks that we need to unlock 21 centimeter science, myself and a lot of other people have said, how do we begin to do this a little more robustly in this end-to-end fashion? And the question I've asked myself is, how can we leverage advances in ML, AI, software, and hardware to make something like this end-to-end forward model tractable for the first time? And it turns out that there is a big chunk of this problem that we can take simply from this kind of acceleration. And so this is the motivation for a paper that I just put out that presents this new framework called BayesLim, which is the first differentiable Bayesian forward model for 21 centimeter intensity mapping to date. And this is giving you a kind of a schematic of what this looks like. The idea behind this Bayesian forward model is to parameterize the signals as they natively would appear, say, in the sky, or for your instrument as a function of the beam angle and frequency, or the antenna gain solutions, and to run a forward model, so to run a visibility simulation, as we typically do when we make data mocks or we do pipeline validation. But in this case, you do it within the wrapping of an automatically differentiable framework. Ones that you may have heard of, like PyTorch or TensorFlow or JAX. And what this allows you to do is to compute model visibilities, and then to compute a likelihood given raw data in a noise model, and then finally a posterior by folding in priors on your parameterization, say prior knowledge about the foreground sky from other experiments, prior knowledge about your beam from electromagnetic simulations, and even prior knowledge about the signal from physical theory. And then to differentiate that posterior with respect to these parameters, right? So we can get the gradients of the posterior very efficiently and very accurately. And this opens up a whole new suite of tools that we have at our disposal, like high-dimensional gradient-aware optimization and sampling, that allows us to do this kind of Bayesian end-to-end forward model and solve this inverse problem in this way for the first time. Another thing that this relies upon is GPU acceleration. So these automatically differentiable libraries make putting this all on a GPU very easy. And of course, this forward model is dominated by matrix multiplications, which is something that the GPU excels at making faster. Okay, so in the last couple minutes here, I'll talk about a proof of concept that I showed in this paper demonstrating this framework. So what we do is we generate a mock data set for a 6-hour Hera scan of the sky. This includes a horizon-to-horizon full sky foreground model that we model with spherical harmonics. It includes a full hemispherical beam model that we also model flexibly with spherical harmonics. And a 21 centimeter signal model that we model in this region of our field of view using this novel formalism that I've developed called spherical stripe harmonics. And the easy way to think about this is a reformulation of spherical harmonics that is both compressed for this specific sky mask, but retains orthogonality and band-limited completeness of typical spherical harmonics. So in total, we have a fair number of parameters. We have about 90,000 parameters between our foreground, signal, and instrumental model. And we adopt priors on them that are fairly reasonable given our current best understanding of the foreground sky, roughly 10%, best understanding of our beams, which I'll talk about, and a very weakly informative prior on the EOR model that basically prevents it from taking on values that would dramatically exceed current upper limits, right? And I'll note that the analysis that I'll demonstrate here was run on a GPU node with 4 A100s for about 20 hours. So this is a fairly modest GPU budget just for this demonstration. Okay, so let me motivate the instrumental systematic that I look at specifically in this paper. And this is one of our leading systematics, which is the chromatic nature of our antenna primary beam. So this was a study led by a MIT PhD student last year, Honggun Kim. He's showing the antenna response for Hera on the left here, and then how that response changes when you make reasonable perturbations to the antenna in the field, like moving the feed in the X and Z direction. And what you can see is that you source these fairly complex response patterns that are complex but seem to be band limited. And so you could imagine modeling this with spherical harmonics as a fairly good way to capture these fluctuations. And so that's exactly what we do in this framework is we use a spherical harmonic basis to model the beam. So what we do is we have some fiducial kind of standard beam shown on top, and then we model it with spherical harmonics, and then we add in noise to those harmonics to generate this perturbed truth beam. This is the beam that we don't a priori know that we're going to try to optimize to, starting with this fiducial beam. Okay, so what about priors? So on the right here, I'm showing you a slice of the beam. And what we know about beams is we think we know our beam fairly well at its maximum gain pointing. But as you go away from that zenith pointing towards the observer horizon, that understanding quickly breaks down. And we think that basically towards the observer horizon, we have an order unity uncertainty on our beam. And this is what that prior is showing, is that as you get closer and closer to this horizon pointing, our prior in the beam is effectively unconstrained, right? And then in black, you're seeing this true beam, which takes on this very complex structure, which is common to see in electromagnetic simulations. Okay, so we want to optimize this, which we can do. I won't talk too much about that, but we want to really sample from it, and we do this using a efficient Hamiltonian Monte Carlo gradient-aware MCMC sampler. And for those who are unfamiliar, the idea here is you're basically using Hamiltonian dynamics of this loss function, in our case the negative log posterior, to make efficient MCMC proposals. Now here's the thing. HMC is kind of the state of the art for high-dimensional gradient-aware sampling, but in high-dimensional and poorly conditioned spaces, even vanilla HMC is fairly inefficient. And so really what you need is you need to precondition it with some understanding of the Hessian matrix, which we show how to do in this paper. In particular, we use block diagonal approximations to scale to high dimensionality, and we use a Cholesky factor to be able to run this Hamiltonian dynamics without having to take the inverse of this matrix. Okay, so here are this HMC no U-turn sampler chains on these three different components. You're seeing a couple of the parameters selected randomly here. With the preconditioning, we get low autocorrelation, which means high effective sample size, and we get about 100 plus effective samples for the EOR component here. So I can show you a corner plot. People like to see this, but again, this is a 90,000 dimensional parameter space, so this is a little tricky. Really what we want to do is we want to project those posteriors into some other representation. Here you're seeing the beam. You're seeing draws from the posterior are a good reflection of the truth beam, and in particular, the RMS of the conditional posterior, shown in blue, is tighter than the RMS of the marginalized posterior, shown in red. And that's really showing that we're picking up on these degeneracies between the beam and the foreground and the EOR signal. This is a movie showing a single HMC trajectory as we walk through the EOR parameter space, showing that we're really, getting at the fluctuations in the EOR map as we do this HMC sampling. But it's hard to see exactly the kind of consistency with the true model, and so we can show that here. These are skewers through that line of sight, and what you're seeing here is that the posterior, shown in red, are really a pretty good description of the underlying truth model in the data in black. And so this really gets at the core of the framework. Is what we're doing is we're estimating the posterior at the field level, at the map level. So we're estimating it as a function of position and line of sight here. And this is different than other estimators that have done this simply in the power spectrum. Okay, and again, we can project this to any downstream summary statistic that we like, in this case the power spectrum, and you can see here that in the modes that we think are not foreground or noise dominated, we do a pretty good job at representing that underlying power spectrum with these posterior distributions. And this is another way of showing it if I just divide by the truth. What you're seeing here in red is the first fully marginalized foreground and instrumental marginalized posterior on the EOR signal. And so this is going to help us going forward to inform us when we're systematics dominated or not. The last question is, will this scale to next-gen telescopes? And that's a big question. And it's very possible that it will allow us to scale to high dimensionality. Compute gets cheaper, and there's lots of room for improvement here. So I'll leave you with my takeaway here, which is that next-gen 21 centimeter cosmology is going to need differentiable end-to-end forward models to really make a truly robust measurement, and I'm eager to see where this takes us going forward. Happy to answer any questions on the chat. Thanks.